sort of replacement sort of mental model. It takes the function application where you want to make progress, and it replaces it by what? By actually the body of the function that we're applying, right? So we're replacing the application of this function, x arrow x times x, by simply the body of the function. So the whole application is replaced by x times x. Not quite. What we need to take care of is that the parameters of the function, x here, refers to the actual argument that we're passing to the function. The actual argument is the number 9. That means we need to replace x by 9 in our application. That's happening in the next step. So we are substituting 9 for x in the body of the function, and now we have 9 times 9. We need to make progress. It's a multiplication. We need to carry out the multiplication, and we're now in a situation where we don't have any further computation to do. We are done in our program execution. So we have taken the given program and found places where we can make progress in each step, and until we finally get to a result of the program. Let me, before we go into more, before we extend the language, let me come up with a factorial example. Function factorial x arrow x, if x is equal to, let's say, 0, the result of factorial should be 1. Otherwise, we have x times factorial of x minus 1. That's the factorial function. We apply factorial to, let's say, the number 4. We do the same thing. We carry out substitutions. We take the whole program and see how can we make progress, right? How can we actually further simplify this program? Actually, I should do the same. The same is the case when we have when we use a function declaration. Maybe we should start with a function declaration first. Function fact x, and we in JavaScript we need to explicitly return. So we have a return keyword, and we have this as the body of the function. But regardless of how you do this, we should be able to step-by-step execute this program. What happens? We handle this whole program using substitution steps. That means we basically eliminate the function declaration. That means we transform this program that has two components, a function declaration followed by the function application. We transform this into a program that just has a function application. But now, this name fact actually refers to the function. It's not really shown in this tool, but now we know that fact refers to this function, and that means we can carry out the application just as you have seen in the previous example. We know that fact has this body, as shown in lines 2 to 4, and that means in the application we replace the application by the body of the function. If you want this to be a bit more dramatic, we can actually add an 42 plus here, and that means we see here, we cannot carry out the addition we need to do this function application. Or if you have 2 plus 2 here, the order is that we first need to now evaluate the argument according to applicative order reduction and carry out the application before we do the addition. But in each step, we look for a place to simplify the program. We simplify this whole program by replacing every occurrence of the name fact by the actual function. And that's happening here a bit implicitly. We don't actually see that this fact now refers to the function, so the tool hides that a little bit. But once you have evaluated the argument, and we know now that we need to carry out this application, we replace the function application with the body of the function. Except that the parameter x is replaced by the actual argument 4. We have a copy of the function body, except that x is replaced by 4. That means we have 4 equals 0, question mark 1, colon 4 times fact 4 minus 1. So each occurrence of x is replaced by the actual argument. So that's a clear mental model, right? So you can study functional programs in this way, and you can, in principle, figure out what any program does by simply keep simplifying the program until there's nothing else to do. So that's basically a clear mental model of how functional programs run. The underlying theory actually is ancient. So this comes from the early 20th century when the logicians, the inventors of mathematical logic, tried to understand what processes we can describe. So they had a mathematical framework, they invented a mathematical framework called the lambda calculus that allowed them to basically describe computation, to describe how, let's say, arithmetic works from a very small number of concepts. The concepts you have seen already, the concepts of the lambda calculus you have seen already in today's lecture, namely function definition and function application. So this arrow is directly coming from the lambda calculus. That's why it's called lambda expressions in all programming languages. And the function, open parenthesis, argument, close parenthesis, that's function application. We call it today, we call it function call. That's the two only components we have in the lambda calculus. Function definition, function application. Lambda expressions and applications. And that's basically how you can think of functional programs to run. Now, in these, a little complication here, I should mention this, a bit of a side issue is recursion. You have a recursive call fact, and this name fact, of course, also needs to refer to this function. What happens if there is no name for the function? Or what happens if we use an, okay? So what if there's no name for the function? I think you've seen that in the previous example. But what I wanted to point out here is what happens if you have assignment in your language, right? So you have then y equals y plus 1, and you have return x plus y. So in JavaScript you would have a let y equals 0, and you have a function f that adds its argument to y, but y keeps incrementing, right? So let's just run this program to see what happens. If you have f of 3, display f of 3. And display of another f of 3, right? So run this program. What you see is 4, 5 in orange. These are the result of the display function, and 5 as the result of the last expression as we discussed last week, right? So if you think about it, substitution will not work here, right? This idea of simplifying the program by replacing names with values bumps into limits when you have assignment in the language. This y here, the y in line 5, actually does not refer to a value in a mathematical sense. Y refers in a way to a place where we find the current value of that y, right? So this replacement will not work, right? So if you deal with this declaration, let y equals 0, we of course cannot replace this y with 0 because y should keep changing. So this substitution is not working. This notion of replacement is not working in a language in which you have assignment. On the other hand, if you don't have assignment, this will work. If you don't have assignment, you run this program, you can actually replace y with 0 in the rest of the program and eliminate the declaration. So replacement works in languages that don't have assignment. Functional programming is defined as a restriction of our usual programming where assignment is eliminated. And that means this way of giving meaning to programs, this way of describing control in programming languages makes sense in this restricted form of programming languages. So what we're looking for is a way to make sense of programs that are written in modern scripting languages. And modern scripting languages have state. They have stateful data structures and variable assignments. They do have lexical scoping, they do have first-class functions, so we need to be able to handle lambda expressions. We need to be able to handle passing functions as arguments to other functions, returning them from other functions. That will all need to be captured in our mental model. But we don't have the luxury of doing replacement, of doing substitution. We need to do something better than that. So modern scripting languages have these characteristics, and what we're after as the first major learning outcome of this course is to appreciate a proper mental model of what happens when programs in these languages are executed. We will also touch upon data structures a little bit. So automatic memory management, data structures can be created, and we don't need to worry about managing the data that we are allocating, and I'll show you that towards the end of this class. As part of CS2104, we will study typing, but we are sort of setting that aside and not dealing with type declarations in this part of the lecture. And that follows the languages that you know. Python, JavaScript, they don't deal with types at compile time. They don't deal with types before you execute the program. So they're dynamically typed. That means the types. That means what is associated with a type are the values that are occurring at runtime. Whereas when you have static typing, we associate program components. We associate the static elements of your language with types. And statement-oriented syntax, I'll talk about return statements later. So, what we're going to start with is a calculator language. I'm going to revise how this program is executed step by step using this new mental model, right? So the CS machine. To repeat, if we have a replacement mental model, this is what happens. We look for a place to make a change. In this case, the multiplication needs to carry out. We carry out the multiplication and proceed. Look for another change, another simplification, carry out and proceed. So that's a substitution way of thinking. Now, when we are in the presence of state, we need to do something better. So here is our CSE machine, our mental model, handling this sort of program. So we do the reverse. We don't look for a place to make progress. We look at the structure of the program. We look at the structure of this whole thing, right? That means we're not looking for the multiplication. We're looking for the addition. That is basically the whole program, as is written here, is an addition. So we treat it as an addition and carry out a step. That means we follow the syntax of the language, up, down, and decompose it into its parts. So we take this addition and break it apart into its components. That leads us to this, to a stack that has the number 1 at the top, followed by 2 times 3 minus 4, followed by plus. That means the next thing to deal with is the number 1. We don't know what to do with the number 1. We set it aside in our CSE machine. We put it on an extra data structure called a stash. Again, we have a component of our program here. This is actually a subtraction. So we need to decompose it into its parts. And that means we get 2 times 3 at the top of our control. So this data structure, this stack, is called control, followed by the number 4, followed by minus, followed by plus. So basically the control tells us what remains to be done. The control keeps track of the actions that we still need to carry out. That's our agenda, our list of to-do items. So this is what we still need to do. And the last thing to do is still a bit complicated, so we need to decompose that into its parts. So that means we decompose 2 times 3 into 2, followed by 3, followed by times. Previously we said we need to deal with 4, we need to deal with minus and plus. So 2, we actually don't know what to do, right? So your mental model has this as a stack, right? Well, it's very simple. It's completely mindless. Think of a primary school student, or even preschooler. You need to sort of tell the preschooler, what are the rules here? Well, the rules are very simple. See what is at the top of your control. and do what it says, what it tells you to do. If there's a number on top of the control, regardless of what else happens, we need to set it aside in a different place. So you can do that on the kitchen table. If you have the number 2 on top of your control, you need to set it aside in a different place. Number 3, set it aside. If you happen to see a more complicated thing, it's also simple to deal with this. Decompose it into its parts. So 2 times 3 becomes the 3 parts, 2, 3, and times. So yeah, well, and the same for these primitive operations. Times is an operation that you tell your primary school kid. Times an operation that takes its arguments from this stash, a different part of the kitchen table. It removes those 2 items, 2 and 3, carries out the application, and puts the result back onto that stash. Yeah? So you see what's going on here, right? Any issue? Do you have any question? In the very beginning, right? You're talking about this first step, right? Yeah. Here it's a bit weird. You see that this expression in the beginning is wrapped in a block. That is. I'll talk about that later. It's basically to handle declarations at the top level. I'm going to discuss that in a few minutes. But that, in this case, will be eliminated very quickly, and you are left with just the original expression in the next step. Oops, but that is not even shown here. So basically, think of this to be just the expression, the given expression. So we start the execution with the given program as the only item on the agenda, the only item on our control. And as computation proceeds, we decompose this into its parts. We'll see many more examples later. So we start the whole execution with the whole program as the only item on this control. And we proceed step by step. And if it's a complex thing on top of our control, no choice, you need to decompose it into its parts. That's what's happening here. More later. All right, so that's basically, I think I showed this to you last week. We're not going to spend more time with this. Any questions regarding the evaluation of such arithmetic expressions in this mental model with control and stash? You may have learned a stack machine, right? So this is a stack machine, basically. We are sort of on the fly translating the given program into postfix notation. So our operators are placed after the arguments, and then we carry out the execution, we carry out the evaluation of these postfix expressions using a stack machine. So that's what's happening here. So you could think of this as somewhat of a compilation on the fly. And you see at this stage, we have actually translated the entire expression into postfix notation. That's what you see here. So 2, 3 times 4 minus plus is the same as the given expression, but just in a different notation. We call it postfix notation. We put the argument before the operator. And of course, you read this from bottom to top in the way this stack is written. So translation on the fly into postfix notation, and then we have a stack machine that finds its arguments on a data structure called a stash. So that's the execution of programs that just consist of individual arithmetic expressions. Let's look at sequences and then conditionals. Now, when the program is a sequence, we do the same thing. We start out with the whole program written enclosed in this block as the only item on our agenda. And then, as usual, as you tell your primary school pupil, no choice, we don't know how to handle this thing, so we need to decompose it into its parts. So if you have a sequence of statements like this, we decompose it following the meaning of JavaScript in this case by taking the individual parts and putting them under control. Except that we put special instructions in between. And these are instructions that allow you to ignore the result of all statements except the last one. So we now have 1 plus 2 as a statement followed by pop, followed by 3 times 4. So you see that we make sense of sequences. So the meaning of sequences is given by this step. The meaning of a sequence in this mental model is to carry out the components of the sequence, to execute the components of the sequence in the given order, where each result of execution is ignored except the last one. And that's what these pop instructions do. So as we continue, we will actually get to execute these pop instructions. That's happening next. You have this 1, 2 plus, and now we have a pop that says, whatever you find on top of your stash, remove it. Ignore it. That's what's happening. And then you have 3 times 4, and we carry out, nothing else to do. At some point in your computation, you may have an empty control. Once you encounter an empty control, there's nothing else to do. Your program has finished properly, without an error, and that means the result should be found on the stash. And there should be only one single value on the stash if everything goes right. So that's the mental model for sequences. And conditionals, we can then study what happens when conditionals get executed in a programming language. We can contrast this with a substitution model. This happens to be in a functional language also, so we can actually run this in a functional language and see how this is executed in a functional programming language. So you have not true, question mark 8, colon, 3 times 4. We need to find a place to make progress. In this sort of substitution way of executing programs, we make progress by evaluating the predicate of the conditional. That means it becomes false. Now the next step you might think is 3 times 4, but that's not the case. We now need to, we cannot decide which way to go. We need to look at the predicate to decide where we want to make progress. So the next step is not to to replace this conditional with false question mark 8 colon 12? No. What we need to do is we need to look at the predicate, decide what to do, and commit on either the consequent expression or the alternate expression. So that means the whole conditional will be replaced by 3 times 4. So that's substitution. So here the rule for evaluation tells you don't touch the consequent or alternative part of the expression before you have evaluated the predicate and before you know which branch to actually execute. That's built into our rule of execution. The same is the case for our CSE machine. So if you run this program in the CSE machine, let's do that. In the CSE machine, we need to evaluate the predicate first. So we need to evaluate the predicate, and after that we need to carry out a branch. So the branch contains the consequent and alternative expression. So in this way, the whole conditional becomes the predicate followed by the branch. We make sure that we're not evaluating prematurely any of the branches of our condition. No, we put the predicate first on our stash, on our control, and need to evaluate it to a primitive value. That value we'll find on the stash, right? Once this predicate is evaluated, its value will be found on the stash. So that's what's happening. We need to decompose the negation. We have true followed by the negation operator. True will be pushed on the stash. The exclamation mark will find its argument on the stash. The negation operation gets executed, and the results gets placed back onto the stash. Now we have a branch on top of our control. This branch needs to check which part to execute, which part of the branch to execute. This branch contains the consequent expression 8 and the alternate expression 3 times 4. Which branch to go into depends on the value of the predicate. The value of the predicate is found on the stash. So this branch instruction in this control pops the top element from the stash, checks if it's true or false. If it's false, it commits to the alternate expression. If it's true, it commits to the consequent expression. In this case, it's false. That means we take the alternate expression out of the branch. It is included in the branch here. Right? We take it out of the branch and place it on the control. And we execute it as usual. So that's how we deal with conditionals in this method. And the most important thing to know is that conditionals are decomposed into the predicate followed by the branch. That allows us to prevent execution of the body of the conditional, execution of the consequent or alternate expression before we know the value of the predicate. That's the consequence of our decomposition rule for conditionals. More examples later. We need to find a way to handle declarations. And declarations need to be treated with care because they need to accommodate assignment. They need to accommodate destructive operations. Let's take a look. We want to add blocks declarations of names, and an example for that is here. So here we have a constant declaration, const x equals 3 times 4, const y equals x plus 2, and y times x times y as the as the example. I'll play with state in a few seconds. So here, I initially removed these parentheses, but when you run the program, implicitly they're added here. That means we can handle this whole program in the way we handle blocks. So you treat the whole program as being wrapped in a block. If there is no block, we put it there, right? So there's always a block that we're starting with. And that means we can give meaning to declarations, even at the top level. A declaration, what is the scope of the declaration? The scope of the declaration is the closest surrounding block. And we make sure that there's always such a block. So the closest surrounding block is the whole program here. So the constant declaration has the scope, the rest of the program. And we give meaning to such declarations and to the notion of scope in this framework by saying a block is evaluated by removing the block, right? So on the control, we want to get rid of the block. But we need to provide for the possibility that we will encounter the names that are declared in this block in the evaluation. And that is done using a data structure called environments. So I gave you all as homework a study of the section 3.2 of the SIGP.js textbook. If you haven't taken CS2104 you were supposed to read that section, 3.2. Let me refresh your memory on how we make sense of name declarations in such programming languages, or statically scoped, block-scoped programming languages. What happens is when we encounter a block on top of our control, the block is eliminated, so we get rid of the block, right? And we just put the body of the block on the control. But in addition to that, we create the data structure called an environment frame. And we evaluate the program with respect to that environment. So what you see here in the middle, sort of in the lower right, you have the left, you have the control, the top right, you have the stash. On the lower right, you have an additional data structure called the environment. So now we have all three components complete. We have control, we have stash, and we have the environment, CSE. So the environment needs to give meanings to names that appear on the control. So whenever we encounter a name in the evaluation of the control, we find the value of the name in our environment, starting with the blue box. So there's always a frame from which we start looking. And that is our current environment. And these frames are linked using arrows. That's also a prominent feature of these languages. The frames are linked with arrows. So then when we decompose this, what's going to happen? We need to deal with this constant declaration first. The constant declaration is treated as an assignment of the given name x. So const x equals 3 times 4 is decomposed into two parts. One is the right-hand side of the declaration in line 2, 3 times 4. The right-hand side needs to be evaluated first. Its result will appear on the stash. Where we see here, 12. And now we have an assignment instruction on our control, assign X. Assignment instructions take their value from the stash and assign and carry out the assignment to that variable, starting looking for the place in the current environment. So we're looking in this environment for the name X. If we don't find it here, we need to follow the arrow until we find a frame in which we have an X, and we need to carry out the assignment. So X happens to be in the first frame of the current environment, and therefore we assign X in that frame to whatever we're popping from the stash. So this 12 will be placed on the stash as a result of execution. Then we have the usual pop, because we don't need that value. We have a constant declaration next, which has X plus 2 as its argument, as its right-hand side. It's decomposed into its parts, and now we have, for the first time, a name in our control. When this CSE machine encounters a name, it looks up the name in the current environment. So it looks for the blue box in the environment. It searches these frames step by step for a matching name. We find actually X already in the first frame. We take that value and put it on the stash. That's how we execute names in this machine. So 2, the same thing, and so on and so on. So you see here how this all works. And in the same way, we can make sense of assignment. So you have, for example, X is equal to X plus 2, and then we just look at X. If you look at this and turn this into a let following JavaScript syntax, you'll be able to see how these environments actually change over time. 3 times 4 leads us to assign X to 12. Pop removes that, but X retains that value 12. Now, if the assignment X equals X plus 2 in line 3 is decomposed into just like the constant declaration, just like let. Assignments are decomposed into the right-hand side, followed by the assign instruction. So X plus 2, that refers to the current value of X, which is put on the stash, 12. 2 put on the stash plus is executed, and now assign X will take that value and replace whatever we have in the current environment under the name X by that value that we have just calculated. That means X is the 12 is replaced by 14, and that means the result of our program is the value 14. So that's how assignment works. Yeah, so I think with that we can proceed to the next topic, which is function declaration and application. Again, the textbook, SIGPGS, section 3.2, it's basically the textbook focuses on what happens in this mental model when functions get applied. It actually doesn't talk about a control or a stash. It focuses only on environments because that's the heart of function application. So let's take a closer look at function declaration and application following this mental model and how the environments look. And I will, last week I admonished you, forget all about stacks in your mental models use the CSE machine. So let's look at the factorial function as an example. So here we have we run and splash. So what we have is the function declaration needs to be carried out first. The function declaration will lead to a binding of the name, fact, to the we'll see that in the next instruction, the assignment will assign fact to the value of the function declaration. Actually, the function declaration is nothing but a lambda expression. So you see that here, function declaration is treated as syntactic sugar for this lambda expression, right? So const fact equal n arrow, well, that's the lambda expression right there. So we treat a constant declaration just as a variant of a constant. We treat a function declaration just as a variant of a constant declaration. So you're making sense of that. We carry out that constant declaration, which will mean that the name fact is assigned to whatever that lambda expression evaluated to. So the value of this lambda expression in control is a closure placed on the stash. And a closure is a pair consisting of the static part, which is the parameters in the body of the function, and the dynamic part, which is the environment in which the function is declared. So the environment needs to be captured, needs to be stored in the function object, and I'll show you in a second why that's important. All right, we have a function application, and now comes the core that you find in section 2.3. What is the meaning of a function application? Well, first of all, we need to decompose it into its parts, right? So the meaning of a function application is all the components followed by a call instruction. The components are listed in the correct order. That means we find them from bottom to top. That means the function expression comes first, followed by all the argument expressions, followed by that special instruction call. Again, in postfix notation. We put that call instruction last to be executed. So the name fact is just a name like any other name. So we look it up in our environment, in the blue environment, and we find that it's a closure, and that's what it is. The number 3 will be placed on the stash also. Now we have a call instruction. That's the core of this machine, of this CSE machine. A call instruction is executed by replacing the instruction with the body of the function we're calling. Where do we find the function that we're calling? We find it on the stash. In what position do we find it on the stash? Well, that's the number after call. Call 1 means the function is supposed to have 1 argument. So we skip over that argument in the stash and find the function to be called. So in the second position on the stash, seen from the right, that's the function to be called. We follow that arrow until we have a function object, right? So that circle, that will show you what is the body of the function. So the result of this function, of this call, will be just putting the body of the function onto our stash, or onto our control. And as opposed to the substitution model that we had for functional programming, we don't do a replacement of the actual of the parameters and replace them by the actual arguments. No, we take the body as it is. This body happens to be just a return statement, so we take the return expression of the return statement and place it on the control. So that's happening next. We just have the body here, the return expression of the factorial function here. And something else happened. We have a new frame. That frame results from extending the function's environment. So we're just lucky here that in the previous step we had the program frame, and we extend that frame. But that's just by accident. We extend whatever frame this arrow points to, and this arrow points at the moment to the current frame. That does not have to be the case all the time, and I'll show you that in just a few minutes. Let's continue this example, and I change the program so that so that you see the differences. So we're extending the function's environment, we're extending whatever this arrow points to, by a binding of the formal parameter, the parameter n here, to the argument. And the argument we find on the stash. So that means we create a new frame in which n, the formal parameter of the function, refers to the number 3 that we popped from the stash. And now we evaluate the body of the function. The body of the function, namely whatever is on top of our control. Decompose as usual, blah, 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 until we have a recursive call. And we call the function recursively. And now, I showed you this last week. This is sort of a bit of a review. And now, what happens is we do the same thing. So we extend the function's environment. And that means this box will get a sibling. And that's essential in these programming languages. So we cannot follow stack discipline. We need to, we encounter, as we go along, we encounter, and we will create a tree data structure. So this is not a stack, but it's going to be a tree as we go along. And finally we get true as a result of the predicate. That means we're done with our recursion, and we can carry out these remaining multiplications and get the result here. Let's change this program a little bit, make it more interesting, right? So this first thing is we need to, we should see what happens when we put this n after the factorial call, because that's going to be interesting. Another modification that I'm going to do is I'm going to have a constant declaration here, const x equals 42. And I'm going to make a block here in which I have a const x equals 7 and the call like that. Why is this program more interesting? Well, we have a local environment in which we carry out the factorial function. In that environment, x refers to 7. So if we're not careful, the factorial call, well, actually what we could do is we could have this as, let's say, the number 1, and we multiply this with x. That should not change the result of the factorial function, but this declaration of x should not confuse us here. Let's see if the result is still the number 6 here. Yep. And that is what we expect when we run this program in the CSE machine also. That means we should see at the end the value 6, yes. But how does that come about? Let's see, let's trace this program step by step. So what we're going to do is we have this declaration of f, and we already see something interesting here. We have a constant declaration of x equals 1 that changes x here, so this x will become 1. And the lambda expression happens to refer to that x. So we need to make sure that whenever we evaluate this x will refer to this declaration, not that declaration down here. How's that done? Well, it's done by, it's done by associating the function that we're calling with the environment at the time, the function that we're defining with the environment at the time of which we define the function. So this name fact is associated with the function object that not just has the body of the function and the parameters, but that also has the environment that we had at the time when we defined the function. So, in other words, the function object has a reference to an environment, and that's the environment that we are extending. And that means when we get to this place, let's go to that place. So we have this block, and in order to make sense of the block, what we do is we extend the current environment with a frame that has space for all the names that are declared in the block. So we create a new frame that has a new x, and that frame now becomes our current environment. So, so with respect, we evaluate now the body of that block, that means line 9 and 10, with respect to this frame. That means we get the usual, we get x becomes 7, and now we have a function application. And now is the place where we need to be very, very careful, right? So what is happening here? We have a function application. Our current environment knows that x should be 7, and we are in danger of placing the body of the function onto our control and keep this as our environment. That's pretty bad, pretty bad. So this is why it's so important to be careful with the meaning of function applications in these languages. This function application, this call, looks up the function, finds the environment in which the function is defined, and extends that environment with a binding of the parameter, in this case n, to the argument, in this case 3. So we have this picture, right? So this is not a stack discipline. In these lexically block scope languages, we need to, we are going to create a tree data structure. And this is specifically important when you have higher order functions, right? You have functions that return other functions, that pass functions as arguments to other functions. You can only make sense of languages that combine lexical scoping with higher order functions if your mental model is appropriate. That means at runtime, functions are associated with the environment that we have at the time of defining the function. The environment can change, of course, with assignment, right? So you could have, for example, you could have here x equals x plus 1. So that is fine. But this x needs to refer to this x here in line 3 needs to refer to this x. And this CSE machine takes care of that. So if we have this, here we run the program. Syntax error. Yeah, of course, this is a constant declaration. So in JavaScript, this needs to be a let now. So we can run this, and we'll see that by the time we're actually executing this this assignment to x, it's happening here. The call gets replaced by this statement, decomposed. So now we are in a position to make sense of this assignment. But we have taken precaution, right? So we are now operating with respect to an environment in which x is that, it refers to that variable here that comes from line number 1. That means the assignment is going to be carried out properly, as you can see here. So we're replacing x with, we're replacing 1 with 2, and we get the proper result. In this case, it's not the factorial function, some other function that gets calculated here. Okay, so that's that. I should also give you an example of higher order functions. So let us take a look at what happens when we have function make plus that takes an argument x and returns a function that takes an argument y and returns, let's say, x plus y. Then what we have, we const plus 1. Const plus 1 equals, what is const plus 1? It is make plus applied to the number 1. And then we apply plus 1 to the number 3. The whole program should evaluate to the number 4, I hope. Yep. And we can now see what this CSE machine does with this program. How can it return functions? And what does it even mean to have functions as values? So here we have the lambda expression, x arrow. The result of that will be that the closure appears on the slash that has now the parameter x and as a body a function that returns y arrow x plus y. You see? So that's the make plus function. We assign the name make plus to that make plus function, and we get this. Now we have the constant declaration plus 1. Its parts. Well, the name plus 1 is going to get assigned to the result of applying make plus to the number 1. Make plus is an application. Make plus closure. And now we are applying this make plus function. So we are extending that function's environment, which happens to be the program environment, with a binding of x to 1 and evaluate the body. That gives us the return value. So, so when we see the lambda expression, we need to come up with a closure that has this environment as its environment, right? So the lambda expression is evaluated by creating a function object and making its environment the current environment. So this blue box will become the environment of the closure that we're creating. That's happening here. And this closure is now valued. In general, we need to get back to our environment here. Why is that? Well, we're done with this function called make plus, right? So what could be the case is that x could be defined at the top level. For example, so let us make this a bit more interesting and come up with a cons x equals 3, and we have an x here. The two x's, one is the parameter of make plus, and one is the x that appears here. So what is the danger? The danger is that if we're not careful, we evaluate whatever remains to be evaluated, which means plus the execution of plus 1, in an environment in which x is 1. That cannot be the case, right? So let's run this program again. We have the assignment, we have the make plus, the call make plus, leads to an extension of the function's environment with a binding of x to 1. And the result of that function application will be simply this expression, y arrow x plus y. So that's going to be the result of calling the make plus function, which is placed on the stash, and that's it. Now we're done with the call of make plus. We've handled make plus. Next on our control is actually, it's still an assignment. We need to assign plus 1 to that closure. That's fine. See that? But before that, we need to do a bit of bookkeeping. See, down the stash, down the control, we have an application plus 1 applied to x. You see that here? We need to be careful that this x refers to the correct value. And we do that by placing an environment restoration instruction on the control. So you can think of a function call to be evaluated by putting the body of the function on control, followed by an environment restoration instruction. Why? Because the call will create a new environment, right? The call will create a new frame. We need to make sure that that frame is properly discarded, and our current environment is restored to the state that we had before the call. So that's what we do here. So as part of this mental model, you need to keep in mind that quite often, or typically, function applications need to lead to an environment restoration instruction to get back to the environment we had before the function call. So let us see where that happens. That happens here. We have a call of this closure. That's our make plus function, we need to make sure that when that call returns, we have an environment in which x refers to 3. Because this x needs to refer to 3. We need to restore that environment. So as part of your mental model, you need to not just make sure that the call will establish a new environment, as you see here, but it will also place an environment restoration instruction onto the control that will tell you what environment to go back to when the function returns. So when we're done with evaluating the value of the function, we have this environment restoration instruction to execute, and that environment restoration instruction has a reference to the environment that needs to be restored, all made explicit in this mental model. So it's very obvious to whoever knows this mental model that that is something we need to do when we're returning from a function. And that means as we get to there, so this is now what the function returns, the result of the function call, this is the +1 value, the result of calling the function make plus, is now on the stash, fine, but we need to restore our environment. We need to discard this environment, so this x1 is not needed anymore. It was only needed to create this closure. And did I say the environment is not needed anymore? I need to take that back. Okay? So that environment should not confuse us anymore, right? It's maybe needed later, but it should not confuse us anymore. That's what we're doing, right? So we are restoring the environment temporarily, as it turns out, so that this becomes the blue environment now. And now we are carrying out this assignment. So we find that this +1 name is here, and we make that +1 refer to the closure. So that arrow here, we have an arrow from +1 to that closure. Now that's an interesting situation. We have a name in our program environment that refers to a function, and that function has as its environment an environment that is different from the current environment. And that's important because when we get to actually call this function, or call this closure, which happens in a second, this is the +1 call down here. This closure refers to that function object, and that function object refers to this frame. So this was not a useless frame. Someone still knows this frame and needs to be able to get back to it. That's what's happening. We are able to refer to this frame, although you guys from Python tutor and from C, although we have returned from the function the frame that you may think it was on the runtime stack. That frame is still there. The runtime stack is not popped, although the function returns, right? So this mental model of associating runtime stack frames with function calls is not cutting it. Function invocations lead to frames, yes, but they're not following a stack discipline. There's no stack here, there's no runtime stack. We have a tree instead. There's a tree of frames. And function values can refer to any frame in this tree. So when we return from the function, that frame may still be alive. It's not a stack. It's some other data structure. It's a tree data structure, and you can have errors all over the place here. So no stack, no runtime stack. So don't believe Python 2. It does something, some visualization like that. It doesn't completely ignore this issue, but it makes it look like it's a stack. It's not. Instead, what we need to do here, we need to, in this case, we have a call of the function, right? And that means that call will extend, well, the function's environment. So the call will follow the closure arrow. That closure will say, this closure, this function object, has this frame as its environment, and therefore that's the one we need to extend. So we're jumping from this frame all the way to an extended frame there. That's what's happening here. We're creating an extension of this frame. This was our previous environment, and now our current environment is down here. That's the environment with respect to which we evaluate the body of the function, x plus y. You can make sense of this program only when you know that we evaluate x plus y with respect to the environment that comes from the closure. In particular, well, y is easy. Y should come directly from the application, right? Because that's a parameter of the function we call it, right? So this function has a parameter y. That's easy. But x is the problem. This x is what the programming language folks call a variable of intermediate scope. So this x is why we're doing this whole business. This x is what we call a variable of intermediate scope. Why is it called a variable of intermediate scope? As opposed to what? As opposed to two situations. One, it's a variable of local scope, right? If x would be declared in that function body, that would be not be a problem, because that's what your C runtime stack will give you anyway, right? The C runtime stack will show, okay, you need to allocate space on the runtime stack for this variable, and that's what this x should refer to. The compiler can put the right instruction there to refer to the runtime stack entry. That is easy. And a global scope is also easy, right? It could be, x could be a global variable in the program. In the C program, you have this global space. What is it called? The C. There's a name for it. Static space, right? So it could be a static variable. No problem, because the compiler can directly refer to that. What is the problem is when you have intermediate scope. It's something in between, right? So this declaration of x is not global and it's not local. It is coming from the surrounding environment. It comes, in this case, from the parameter of the surrounding lambda expression that surrounds this lambda expression. So this x is a variable of intermediate scope, and our CSD machine handles this properly. Okay, well, that was the core of this whole business. The restoring environment becomes important when we have, and the same is the case when we have blocks, right? So let me go to the block example. You run this program, and the same thing will happen when we exit a block. So in this example, we have a block in which x is 42, but the outer block says that x is 1. So when we start running the program, we allocate space for 1. Eventually, you will need to deal with that block. Let me turn on the flash here. Eventually, we will need to deal with this block from line 2 to line 5. That's this block here. We need to make sure that when we're done with that block, we go back to the previous environment, right? So that's another application of this environment restoration. When a block is exited, we need to make sure we restore the previous environment that we had when we entered the block. So that's the purpose of this env instruction here. The env instruction makes sure that when we exit the block, the previous environment is restored. So we have this x in the body, x becomes 42. We have the display, and now we have a call of display. Okay, good. Let's do that. And now we have an environment restoration instruction that needs to be done before this display is executed, right? We need to restore the environment so that this display will display the number 1 as opposed to the number 42. So that's what's happening in this restoration. We are restoring the environment in which x is equal to 1. Good. That's restoring environments for that. Restoring environments for functions, we have seen that. You take a closer look. I don't have time to explain the subtle details here. But you put the multiplication behind, and that will show you why we need to have restoration instructions after the function call, right? Because this n cannot be the n of the caller, right? The caller frame, a factor like n minus 1, will give rise to a new n, but when that call is done, we need to restore to the old n. And that's another use of the environmental restoration instruction. So please take a good look at this, and I will come up with an exercise that will make you form your proper mental model. So I'm going to come up with an assignment that will force you in a way to make this your own mental model for execution of programs of this kind. All right, return statements. There's something weird in these languages that have explicit return statements. In functional programming languages, again, we have a simplification. Most functional programming languages are expression-oriented. That means there is no such a thing as statements. The body of a function is an expression. And when you call a function, implicitly, what that means is the result of the function is the result of evaluating that expression. There's no discussion when you return from a function. The return value of a function in functional programming is whatever the body expression evaluates to. These statement-oriented programs are different. In a statement-oriented language, at least when they have explicit return statements, you can return from anywhere in a function. And that causes a little problem in our mental model, as we're going to see in a minute. We're going to have stuff in our control that shouldn't be there. We'll see that. We're going to encounter that stuff in a minute. Depending on the value of b, we either return 2 times x, or we return x. So let us see what happens when we evaluate this program in our CSE machine. You run the program. This is a function declaration. It gets on the control as usual. We have a lambda expression here. The lambda expression will give us a function object that you see here. And we have a pop, a function application. And now we're getting close to the truth. The function application, f, true, 7. Now we have the call. Now this call will replace, the call will be replaced by the body of the function. So far so good. The body of the function consists of 2 statements. So we're going to have a sequence of 2 statements here. We have this return, 2 statements. We have a conditional statement followed by a return statement, right? So this conditional statement followed by a return statement. So we decompose that into its parts. So we have the conditional expression, the conditional statement, followed by a pop, as usual, followed by a return statement. Now the weird part is this return statement in the blue box. The return statement in the conditional may force us to ignore the previous return statement, to ignore the return statement return return what? Return 2 times x, right? So this return 2 times x may never be executed, but it's under control. How can we prevent it to be executed? That's the adjustment we need to make on our mental model. We need to change the mental model so that we have the power to ignore this return statement where necessary. How do we do that? You already see it here. What is our instrument to make that happen? Anyone? You all still paying attention? There's only a couple of minutes left. Mark, yes. The mark instruction actually takes care of that. So we have a mark instruction that we put on our control before we actually place the body. So that's what's going to happen here. With the call of functions that are a bit more complicated, we call it complex functions. The call of functions in which weird stuff happens with return needs to be prepared to return prematurely. That means it needs to take care that we remove stuff from the control when we have to. And that's the case here. So the mark gets placed on the control as a marker that allows us to remove instructions. That's what's happening here. So we put the body there, but we put also a mark here. So in case we prematurely return from the function, we clear everything until the mark. That's what we do. So when we get to the return, in this case B happens to be true, and that means we execute the statement line 3, and we have this nasty return still there. So this branch return will force us to execute return x. Return x, the return statement now needs to be modified. When we have such a return statement, we need to, of course, put whatever result of evaluating of the return on our stash. So x will end up on the stash. What is x? Not on the screen anymore. X is 7. So 7 will be on the stash, like this. But this return now removes everything between the return and the last mark. That's what's happening here. So boop, 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 gone. And now we're done. Okay, so that was the nasty stuff with general return statements. So we skip the rest of the function using markers that we place on the control. The solution is a mark that we place on the a marker that we place on the control that allows us to remove all control items that were pushed after the last marker. Further language features: tail recursion. What happens when whatever you want to return is the result of a function call. In particular, the result of calling the function that called this expression. You can exploit this by implementing tail recursion. It's a little detail, not so super important for this course. But this notional machine is naturally tail recursive. That means we can easily accommodate what people in this SIGP textbook make a big deal of, iterative processes. Those CS2104 students will remember that. So iterative processes are implemented in this notional machine as tail recursion. So we can play and see how we can make sure that no space. Remember space consumption, right? In CS11S, we made a big deal and said, iterative processes don't give rise to space, right? But what is that space consumption? It's actually space consumption on the control. So iterative processes, if you're careful and doing it right, will make sure that no space is consumed in the control. No matter how deep your recursion is, the control remains constant. And that is a feature of this type of mental model, if we're careful. That's tail recursion. Exception handling. What could you do? Imagine. So this is just the last question that I have for you guys before I let you go. You remember exception handling from last week, right? We want to deviate from the usual flow of control. We've already seen a way to deviate from our usual flow of control just now, right? Because these return expressions, these return statements, in some sense, deviate from the usual flow of control. Whatever is under control, we need to ignore and prematurely return from the function. Is that right? We need to, and actually, functional programming people hate this feature of imperative languages, right? So in the history of computing, we have the gurus telling us, don't use this particular construct. Famous is goto, right? So goto is a construct in languages such as C that let you jump from one place to an arbitrary different place. All hell can break loose when you do that. Don't use it. All your teachers will say, goto, don't use it, right? So there was Dijkstra. Edgar Dijkstra came up with this slogan, goto considered harmful. Goto considered harmful. Don't use that construct. So it was introduced by the early pioneers because machine languages let you do goto, right? So why don't we have it in our high-level language? Bad idea. The same, the functional programming people will tell you. Return considered harmful. Don't use it because semantically it has its complications. Try catching something like that, right? It deviates from the usual control flow. And we have already a solution, namely, that is really the last question today. What is the solution to this issue? What do we need to do in order to properly implement try-catch in this CSE machine? When we imagine you need to execute S1 and S2, but we don't really know if we need to execute S2, right? So we need to execute S1 until we get an exception. And in that case, we need to abandon whatever we have done as a result of S1. All the stuff that is accumulated in control, deep in recursion, you could have a huge control stack, and the exception occurs. And now you need to get rid of all that stuff you have under control to get to S2. How do we do that? Mark, that's right. So we put a mark on the control. That tells you, okay, an exception will clear all the stuff on the control, get back to the right place, and install S2 on the control. All right, so that was basically it. I'm not going to talk about scheme. And not going to worry about this. Concurrent programming, you can extend the CSE machine by concurrent constructs and add threads. We're going to talk about that later in the course. Any questions, anyone? I hope for those, especially the non